Welcome to this short demonstration of the MS Health 2 project. We have created a generalised system for modelling an emergency department, including a machine learning model to predict attendance. Our team consists of Ethan Wood, Wu Haoshen and Noan Luanar. Noan is now going to explain some of the backgrounds to the project and our key requirements.
We aim to create a generalized system to allow the modeling of any emergency department within an evaluation framework. A user can write a model in Python where, once uploaded, it will be run against historical patient data to gain a score for each particular metric. The system then automatically manages and scales models whilst providing a simple Python object interface to patient data. One of the provided models is a machine learning algorithm of emergency department admissions with improved accuracy over the current admissions prediction system. The framework will include a graphical user interface for interacting with the models and a RESTful API to request and retrieve data. As a result, our requirements are creating a machine learning algorithm to model admissions of emergency department based on historical and third-party data, designing a generalized system for modeling an emergency department, creating a RESTful model endpoint to allow integration into existing infrastructure, to build a centralized database to contain model information and our predictions, to make a dashboard to interact with the models, display business information, and have additional visualizations for data, to ensure the utmost secrecy and security of our data, and finally, strive for complete and accurate documentation of our project's components.
The easiest way to understand our system architecture is to look at the typical flow of a user through our system. This starts with them having an idea of a particular hospital metric they would like to predict, for example wait times or admission numbers. They then develop this model within the Azure Machine Learning Workbench and package it into the template file provided. The packaged model is then uploaded to the model dashboard running Node.js, which builds a Docker image and stores it in blob storage. The Docker Swarm cluster takes this image and automatically manages it to complete tasks requested by the user. A task could be to evaluate the model between two dates or to run it in real time. These are stored on the Postgres database along with the historical information such as patient data or weather. Hospital infrastructure can access the model results via a RESTful API, which is also used to show this information in a user-friendly dashboard. The three main technologies we used were Python, Postgres and Node.js. Wu Hao is now going to cover our machine learning model.
Our model is based on a concept called recurrent neural network. Due to its unique structure, the network has the ability to detect dependency in sequential data. This means they intend to find correlation between different points within a sequence. There are two kinds of dependencies, short-term dependencies and long-term dependencies. The ability to find such dependencies makes it possible for the network to recognize patterns in sequential data and use this information to predict a trend. In addition, we prefer this network to other methods such as RIMA because it outperforms them all in terms of accuracy. Now, let's look at the network structure we chose. Our network is a three-stack GRU network, which obviously composed of 3 GRU layers, with each layer containing 16 GRU cells. The input is a vector of 250 steps of history, which is roughly 3 weeks of data. The input is then go through the network, and it will produce a vector of 6 scalar values, which corresponds to 6 steps into the future, which is our final prediction. We also apply a recurrent dropout of 0.5 to regularize the network to avoid overfitting and to improve the network's ability to generalize instead of memorize the data. The model is implemented using TensorFlow as it is much easier to write the model, to test the model, and to deploy into production.
Our front-end is a dashboard that aims to create a user-friendly interface for models. Thanks to our upload system, we give users who develop their models automatic packaging and uploading to blob storage. This happens with a Python packaging script, which extracts the models into a new folder, copies the framework files, reads information from the model files, and builds a Docker container. All the while, log files are generated at regular intervals to track the progress and success of this task. The processing time goes from a few minutes for simple models to several hours for ones with very complex requirements. For an overview of technologies, our dashboard is a web server built using Node.js with Express.js as a web application framework for the routing. We use a vast array of NPM libraries such as bcrypt to create the authorization system. The data visualizations were done with React, our packaging and scripting was done with Python, and the containerization was done using Docker. This is a quick demonstration of our front end. So here we have the landing page of our dashboard. We'll log in as an administrator user, and that gives us access to more features. Here we have the initial page of all the model information, so we have access to every crucial information we'd want. We get to show more models. We can search through anything we want, say busyness. We can also click on any specific model to gain access to its full information. So, for example, here we have model 47, so we have access to the information of just this model. If a model's been run or evaluated, you're able to see its progress, so this model's been done. Here you have the command dashboard, so you can disable, delete, get the logs, reset the models. Here you have the 3 methods to interact with the database, so creating a new event, seeding the model, evaluating the model. All of these changes will be reflected onto the dashboard. Here we have a nice visualization to see the prediction and the historical data, which we can update with any data we want. Example, here we have access to the prediction and the historical data through tables if we want to see any specific values. We can also see the logs of any specific models, so this allows us to track the progress of any models, and any errors will be reflected into here. We don't see, we have a profile, so any models attributed to one specific person will be visualized here. If you're an administrator, you'll be able to create and delete users. And finally, we can upload models through this page. And so this process has been sped up because it's slow, but here we can see the progress and the animations of the conclusion.
The model swarm uses a custom system we're calling event-driven Kubernetes. I'm just starting the system now, and it first clears all author models before loading the new models from storage. These act a bit like serverless functions, as our system monitors the number of requests for each model, and it automatically spins up additional nodes before they see an excess load on one model. I have now requested that the departure model reseeds all data from 2016. The system is now going to automatically spin up additional nodes based on that demand. This is faster acting than traditional Kubernetes, and better when models might be waiting for some resources such as network, which are not traditionally monitored. As you can now see, additional nodes have been automatically created. Writing a new model is easy, and in most cases only a few lines of code. We have a complete documentation covering all aspects of our system. Wuhao is now going to summarize our achievements.
Although we shifted our main point of focus from the deep learning model to this generalized system and changed our mask list accordingly, we have managed to finish 95% of must-have, 86% of should-have, and 68% of could-have. For the must-have part, we created a deep learning model capable of predicting the future attendance, a general system for the ER with API endpoint, a centralized database, and a dashboard. The alert system was also partially finished. We also have taken rigorous measures to ensure the security of our system. For the should-have, we have finished most of them, including integration of third-party data, integration of the deep learning model into our system, and simulation server to test the model. For the could-have finished most part as well, including test suite, performance tuning, and additional visualization. Furthermore, we documented what we think could potentially improve this project in the future.